All right. So then let's start with a reminder item, homework number 1. It's due next Thursday. I think about half of you guys have already signed up on Expert here, and some of you guys are already working on the problem. So if you haven't, make sure you sign up probably today or over the weekend and start working on the problems. Okay. All right. So let's continue. Chapter 13 today. Let's see. So last time we talked about temperature. We gave out the definition in physics. It's the high value of something. We call it with hot object, and low value of something that is called temperature. Okay, and then for temperature, the SI unit is Kelvin. All right, just keep that in mind. It's not Fahrenheit. It's not Celsius. And we talk about different scales. You can actually convert from one to another. So the formulas you need, you can find them here. Okay. This is from Celsius to Fahrenheit, or the other way around, and then also from Celsius to Kelvin, from Kelvin to Fahrenheit, and then all the other ways around. Okay. We also talk about for the low temperature, there's a limit of 0 in Kelvin. That is the low limit. But for the higher limits, there's no higher limit. You can go as high as you want. Okay. Or as high as you can find. From Kelvin to Celsius, then it's simple. Just add from Celsius to Kelvin, you just add 273.15 to the temperature in Celsius to get to Kelvin. Okay. Today we'll be talking about thermal expansion of materials. Okay, and if we have time, we can also talk about gas law. I think you guys will all know that material expands. So for example, if you see probably not so often in Mount Vernon, you see a bridge have joints like this, but like in cities like in New York City, or like when I was in Chicago, I saw a lot of these bridges. So then there's joints here, there's like gaps here. This is designed to, when the temperature changes, it will expand or shrink. Okay, so then you need this gap, like I kind of act as a buffer. Okay, so when it's expand, it doesn't crack. Okay. But I think other phenomenon we see often is like the one down here, potholes. We see them very often in Mount Vernon, I guess. So typically in winter, when temperature changes a lot, when the concrete expand and shrink so often, so then you create stress in the material, then it cracks. Okay. All right. So basically, if you put into formula, which we like in physics here. So typically, like so if there's a change in the quantity, we call it delta L. This is change in length of the material divided by its original length, say L. Okay, then it's proportional to the temperature change. Okay, delta of T. That's referred to change in temperature. With the coefficient here, we call alpha. It looks like A, but it's alpha. All right. So this alpha is associated with the material itself. Okay, so different material have different alpha here. But if you rearrange the equation here, you'll see that alpha is equal to delta L divided by L, and then divided by the change in temperature T. Okay. So alpha is called the coefficient of linear expansion. All right. So if we just focus on the expansion in one dimension, then we call it linear expansion. All right. It has an SI unit of Kelvin inverse. Okay. You can see from here, from the formula up here. So delta L will be having a dimension of length. L will be also having length, so that cancel out. But delta T will have dimension of temperature, which has unit of K. So then 1 over K will be the dimension. All right. Or if you use Celsius, then it's inverse of Celsius. Okay. All right. Now, as I mentioned, if you have different materials, then you'll have different coefficient of linear expansion for the material. Typically for, you can see from the table here, for metals, they will expand or shrink more significantly than the other materials. Okay, so it has higher coefficient of expansion for metals, and then for other stuff, you kind of having lower coefficient of expansion. Okay, but anyway, it's these coefficients of linear expansion are in the order of 10 to the -6, so they are relative small numbers. Okay, so even though you could have temperature change, say like 20, 30 degrees Kelvin or Celsius, you might not necessarily notice just by eye. Like take a look, the visual change is very small still. Okay, but we are going to do a lab here on this next week. Okay, so next week's lab, we are going to do expansion, thermal expansion of materials. We will take 3 different metals, and then we will see the amount of the length change. Okay, so we'll see that in the lab. All right. Another application of thermal expansion that was used often was this type of thermometer called the bimetal strip thermometer. So you actually have 2 types of metal, A and B. All right, they are welded together, originally having the same length. Now, if you have temperature change, say if the temperature is low and when it's cold, so then this guy shrinks at the bottom here, the amount is different from the metal above it. So then it will bend it. Okay, so that's how. So the needle here is, or actually the coil here is made of by metal strips. So then it will make the needle move to point at different scales. Okay, so that's one of the applications. All right, so so it's clear that material can expand one dimension, like if you have a very thin material. Now, if you have a 2-dimensional material, say you have sheet of metal, it will also expand now this time in both dimensions. Okay, so say in vertical and horizontal direction. Say if you have a hole like this, if there's a plug here, then you will expand both the hole and the plug will expand. Okay, if you remove the plug, the hole will also expand. And then the outside will also expand, okay, if temperature increases. All right. Similarly, for a 3-dimensional material, for example, if you have cubic, then if the temperature increases, the cubic will also expand, but in 3-dimensional. Okay. Let's take a look the example of 2-dimensional expansion here. Okay, so it will turn out that the change in the area, because now you have 2-dimensional expansion, so you are focusing on the areal expansion here. The change in area is approximately equal to twice times alpha, which is the linear coefficient of linear expansion or 1-dimensional expansion, times the original area of the material times change in delta T, in the change in temperature. Okay, so let me show you guys the algebra of this. Let me stop sharing here so I can my screen over here. All right. So let's take an example of a square. If you have a square, okay. So let's take a look here. Now this is at original temperature T0. Okay, so you can say T0. Original temperature, say whatever, probably like 25 degrees Celsius, maybe. Now, if you increase the temperature up, right? Say, for example, 25 degrees Celsius, if you increase it to the final temperature, say, for example, 75 degrees Celsius. Okay, and this is just an example, but in this case, the change in temperature then would be the 75 minus 25, which is 50 degrees Celsius. Okay. So when you heat up the material, it will expand in vertical direction by the amount of, so let's say the original dimension here, this is L. for the square, this is also L. All right. Now, according to the expansion in one dimensional, we know that this is going to expand by the amount of delta L, right? And then delta L, according to one dimensional expansion, that should be equal to alpha times L times delta T, right? If you go a couple of slides back when we define the coefficient of linear expansion, this is what it is, all right? Now, this is in vertical dimension. Also in the horizontal dimension, you'll expand the same amount of delta L, right? Because expansion happens in both dimensions. Now this will be your final shape, kind of look like that, okay? In reality, I don't think you will be able to see the visual expansion. It's very small, okay? It's 10 to the minus 6 order, so it's not easy to see it, but this is like kind of zoom in there, okay? So then the change of area will be the one shaded in red here, okay, compared to the original one, okay? So let me call it the final area to be A prime, and then the initial area to be A. So we know initially for the square, the area should be L times L, which means L squared, right? For the final area, this is going to be L plus delta L, right? Times L times plus delta L. So L plus delta L squared. Okay. Now we can see, we can expand the square here. So it becomes L squared plus twice of L times delta L plus delta L squared, right? So when you expand the square, it becomes 3 terms. All right. And we know that this change in this alpha is in the order of 10 to the minus 6, right? So this is something like 2 times L times 2 times L times something, a number, say, let me see. Let's take like 10 maybe, 10 times 10 to the minus 6, which is alpha times L times delta T, right? So the second term, this guy becomes this, all right? And then L squared remains here. So this equals to that. And then plus delta L squared, delta L will be 10 times 10 to the minus 6 times L times delta T. And then you square it, right? So when you square it, the 10 minus 6 becomes 10 minus 12, right? So this term, the third term here is in order of 10 to the minus 12. Compared to this guy, the second term is in the order of my 10 to the minus 6, right? So this can be very small, okay? When you have something like L squared plus something times L squared, and then this times L squared, right? We can ignore this, the second order smaller term, right? So you can take this out because this is very small. So then your A prime is approximately equal to L squared plus just this term, right? The first order approximation, the first order, this is called the second order, okay? So this is the first order approximation. In mathematics, this is called first order approximation. This is called second order, okay, approximation, okay? So then you can ignore the second order or the third orders, okay, if they are small enough. So this is approximately equal to L squared plus 2L times delta L, okay? And we know that delta L, so this is approximately equal to L squared plus 2L, delta L will be alpha times L times delta T, according to the definition earlier here. Delta L is equal to alpha L times delta T, okay? So then this is what you have. This is your final area. Okay. Now let's take a look at the difference, the change in the area. So for the change in area, right? Delta A, that should be equal to final minus initial, okay? So final is L squared plus 2L, or actually approximately equal to that, okay? Not exactly because there's a higher order we ignored. Times alpha times L times delta T, okay? This is times. This is A prime, so this is A prime minus A which is L squared, right? Just minus A there. So then you can see this one cancels out. Okay, L squared cancels out. So then your change in area is approximately equal to 2 times L times alpha times L times delta T, which is equal to twice alpha times A, because you have L times L, which gives you L squared. That's equal to A, the original area, right? Times delta T. Okay. So then your change in area delta T is equal to approximately equal to that, okay, which is the one that shown on the PowerPoint slide. Delta L approximately equal to 2 times alpha times A times delta T. Okay, so then this is your conclusion there. So you can see if alpha is a coefficient, is a constant number, then 2 times alpha is also a constant number, right? So changing area, then the two-dimensional areal expansion is proportional to a coefficient, which is equal to twice of the linear expansion times original area times the change in delta T, okay? Let's go back to the PowerPoint slide. So this is the result here, okay? Now, let me see. Any questions you guys have? All right. So you can also, so this is two-dimensional expansion. So it's just twice of linear expansion, okay? Coefficient of linear expansion times the original area times delta T. Similarly, for three-dimensional expansion, you can do the same algebra, just a little more turns when you expand this time when you are looking at volume, you actually do the Q for a cubic, okay? So there's a lot of more turns, but you can just keep the first order approximation like the turns that has delta L, and then you can ignore the higher orders, the delta L squares or the delta L cubes, okay? So at the end, you'll again arrive at this conclusion that change in volume or the expanded volume is equal to a coefficient times the original volume times the change in temperature, where this beta will be equal to, in this case, because it's three dimensional, then it's equal to 3 times of the one-dimensional coefficient. Okay, so 3 times alpha, beta equal to 3 alpha. Okay. All right. Now, as I said, generally you expect that when temperature increases, volume expands, right? But there's one exception here you might encounter is the water. Water is very strange, okay? It actually behaves very strange. So in the temperature range from 0 degrees Celsius to 4 degrees Celsius, okay? If your temperature increase, actually the volume decreases, okay? Because the density here increases, that means volume decreases, okay? So this is one exception here that you will encounter for water at this range from 0 to 4. When temperature increases, the volume actually decreases, okay? But other than that, when you are over 4 degrees Celsius, then as temperature increases, the volume increases, so the density decreases. Okay, so the fact that here it shows density decrease, that means volume actually increases. So that's the same as other materials. Okay, but anyway, this change is again very small. Okay, so it's in this range, like percentage wise, 0.0075. Okay, it's very subtle there. All right. So the expansion of material, you can actually sum up the knowledge if you know. Then you don't have to panic so much in winter. Okay, when your gas meter sets low, because in that case, the gas actually shrinks, right? So that means for the same amount of volume of the gas, when it hits low in your reserve, actually it will go further miles in summer when it's hot. Okay, so when summer is hot, that amount of gas reserve is it's less. Okay, but still you should find a gas station as soon as possible. Okay, don't call me and then tell me you say it's going to go longer, but now I'll run out of gas. All right, just yeah, some tip there. All right. So let's take a look on one example or exercise here. So this says early in the morning when the temperature is 5.5 degrees Celsius, gasoline is pumped into a car's 53-liter steel gas tank until it's filled to the top. Okay. Later in the day, the temperature rises to 27 degrees Celsius. Now, the volume of gasoline increases more for a given temperature increase than the volume of the steel tank. All right, it's asking you, let's see. It's asking you how much gas will spill out of the tank, okay? Now, there's a table, there are two tables here. I think we saw one table before, we saw this table before, right? These are referred to solid, okay? So these are all solid. Now, when you have liquid, okay, so just compare the numbers, you'll figure that for liquid, they actually expand more than the solid. Okay, solid is like 10 to the minus 6, but liquid is just in 10 to the minus 3 orders. Okay, so most liquid, they will expand more than solid if their original volume is the same and then they start at the same temperature. Okay, or given the temperature change is the same. Right. So in this case, you probably like doing something similar to this one, but three-dimensional wise, right? So the tank will expand smaller than the gasoline. So you want to see how much volume changes the gasoline, and then you want to see also how much change in volume is the tank. The difference between the two expansions will be your spill of gasoline out of the tank. Okay. So I'll let you guys try to figure out this in a few minutes, then we can take look at the solution together. Also keep in mind in the two tables, this one gives you coefficient of volume expansion already. This one just give you linear expansion. So that means for volume expansion, you want to multiply these numbers by 3, right? Because you are looking for the volume expansion there. So basically, what you need to figure out is you use this equation. The change in volume is equal to beta times V times delta T. Okay, V is the original volume given, so V here is the 53 liter. Okay. And then it says delta T should be your final minus your initial temperature, right? Now beta for each material, you will have to look up it up in a table. Beta for the steel tank, okay? Here, for steel, it's the iron. So iron is 12 times 10 to the minus 6, all right? But because this is linear, it gives you just linear, so you want to multiply by 3 times that gives you beta, okay? In the dimensional Kelvin's inverse. Now, beta of gasoline, it's in the next table here. Gasoline would be, this time it gives you already the volume expansion coefficient, okay? Then you'll be comparing delta V for the steel tank and then delta V for the gasoline, okay? The difference of the two will be your spill amount. All right. So I think I see quite a few responses here already. We can take a look here. And many of you guys actually get the right answers here, so which is a good sign. So you can do like change of the steel and then change of gas individually, or you can just say I want to just take a look at the difference. Okay, delta V gas minus delta V steel. All right, now delta V gas, then that will be equal to beta of gas times the V times delta T, right? Minus delta V steel will be beta of steel times V times delta T, okay? If you are doing this way, then you can single out or factor out these two because they are the same, right? They are original volume and then the change in temperature, they are the same. So this would be then just beta of gas minus beta of steel times the volume, initial volume times delta T, okay? Now let me stop sharing now for you guys online can see better that way. All right. So then now you can just plug in the numbers here one time. Okay. So this is 0.95 times 10 to the minus 3 Kelvin inverse minus 3 times 12 times 10 to the minus 6 Kelvin inverse. Okay. Times 53 liters times delta T, which is that one minus that one, that would be 21.5 degrees Celsius. Okay. So 21.5 degrees Celsius then. All right. So then now you can plug in your numbers into the calculator. It will tell you this is 1.04. Okay, if you keep 3 digits, then that will be your answer there. Or if you say you want to keep 2 digits because the numbers given in the problem, they are 2 digits. So then approximately like 1.0. Okay, so that will be your final answer there. You might be wondering about the consistency of the units, okay? Because here it gives you Kelvin inverse. Here you have degrees Celsius, okay? Now, you don't have to worry about Kelvins and degrees Celsius because they are the same scale, right? I mean, the change in temperature, if it's 5 degree in Celsius, it's also 5 degree in Kelvin, okay? Because from Kelvin to Celsius, you might simply just minus 207.7315, okay? And then the other way around, if you go from Celsius to Kelvin, you just add the 273.15. So then change in Kelvin and change in degrees Celsius, they are the same, all right? Now you do have to pay attention to the units difference if one is given in Kelvin, one is given in Fahrenheit, okay? Those are two different scales, okay? Meaning change in temperatures are different from one scale to another one, okay? So if it's degrees Celsius and Kelvin, then that's fine. You don't have to worry about it, okay? Because here you can convert the final temperature to Kelvin and then initial temperature to Kelvin, right? So simply then it becomes, the first one is 27 plus 273.15. That's the temperature in Kelvin, right? Then you'll minus 5.5 plus 273.15, right? That's in Kelvin. So this and this will cancel out. So then that will give you also the 21.5 degree in Kelvin, right? Because this is now in Kelvin, this is now in Kelvin, okay? So when you see the units like Kelvin inverse or degree Celsius, then you don't have to worry about that unit conversion there. Okay, because anyway, they will cancel out. So that refers to when you are working on the difference in temperature. Okay, so just keep in mind, if your temperature, you are looking for the change in temperature, then you don't have to worry about that. On the other hand, so for example, for gas law we are talking about later, I guess you guys learned this already in chemistry. So ideal gas law, PV equal to nRT, but we'll get to the derivation just in a few seconds, okay? So in this case, if the temperature is given in Celsius, all right, in the equation here, you are not talking about change in temperature. You're just talking about just temperature. Then when you want to plug in the numbers into a particular equation only, okay, when temperature is concerned, then you want to convert that into Kelvin first, okay? Otherwise, the equation will not, or otherwise it will not give you the correct answer, okay? When you are doing change in temperature, then degree Celsius is the same as Kelvin, okay? So just keep in mind, if you are doing change in temperatures, then degree Celsius and Kelvins, they are the same, all right? You don't need to worry about the conversion of the units there, okay? But otherwise, if just temperature, then you will have to convert, okay? From degree Celsius to Kelvin, all right? Any other questions you guys might have on this one here? All right, then we'll move on to check the ideal gas law. All right. So ideal gas law, when you guys learn in chemistry, I guess you might not think about the application, but it actually has quite some application. So for example, like hot air balloons, okay? So that was I know Ohio is known as the birthplace of aviation, but the first time people were using, when people were in air, traveling in air, it was actually used a hot air balloon. Okay, so that was in France. Okay, like a couple hundred years ago. So yeah, a little bit more than 200 years ago, 200 like 40 now years ago. Okay, and then in the very ancient time in China, in the Three Kingdom era. So this is not the modern version of it. Okay, it's called the lantern, military lantern at that time. So that was used for military services. Okay, so you guys can buy this thing. I guess in Amazon or something. There's a candle here. You can light it up, and then it will heat up the air here. So then this can be floating in the air. Okay. So a couple of years ago, my neighbor actually was playing this with his kids. So that was very fascinating. It was my first time seeing that in action. But yeah, that was pretty nice. All right. So first, let's talk about gas. Okay, so gas is the easiest state of matter in science here to study. But the real gas actually is very complicated. Okay, so in theory, when you are studying something, you want to start from the simple configuration, right? So to start with, then we will just assuming that the gas molecules are just point particles. Okay, so take a look on these ones here. So you can just treat them as a small sphere, and then they are very far away from each other. So then the interaction between them, like intermolecular interactions, we can ignore them. Okay. Now in reality, for the room temperature air, okay, actually you can treat it pretty much as ideal gas because it's very thin. Actually, the molecules between from one to another actually is far enough compared to their sizes. Okay, so for just air here we are breathing in and out. You can actually treat them as ideal gas. Okay, so let's start take a look at an ideal gas which is thin enough and then far away from each other, so we can ignore the intermolecular interaction. Okay, to describe ideal gases, you need to have a few physical parameters. Okay, one is pressure, which we learned at the end of last semester. Pressure is equal to force divided by area under influence. And then it has SI unit of Pascal, okay, or newtons over meter square. The second physical parameter we need is called temperature, which has SI unit of Kelvin, okay. Volume has a SI unit of meters cube. So pay attention to these SI units, okay. So a lot of times you might not be getting pressure in Pascal. They might be in, say, like how many millimeter of mercury, or maybe how many like ATM, which stands for atmospheric pressure, okay? Or sometimes like how many bar, that's like 10 to the fifth Pascal. Temperature, a lot of times you are given in degrees Celsius, pretty much in science. That's the units that being used a lot, but it's not SI unit, okay? And then volume, a lot of times you are given, say, like liters. Okay, so liters is not meters cube. 1 liter is 1,000th of meters cube. Okay, just pay attention to the units there. All right. The last quantity you need to describe the ideal gas is called the number of atoms. Okay, so if it's referring to just number of atoms, then you use capital M. If it's referring to how many moles of substance, then it's a small n. Okay, I think you guys know learn more already in chemistry, but 1 mole it's equal to 6.022 times 10 to the 23, okay, of atoms or molecules. Okay, that's the number. All right, now let's take a look here. We'll check like the relationship between these parameters one by one, and then hopefully we can see if we can come to a conclusion. Okay. Now, a lot of these are coming from our daily experience or the experimental results. Okay. So first, I mentioned this last time that in olden days, people use thermometer called gas thermometer, which means you fix the volume of the gas in the container, and then you'll be reading the pressure here by taking the level difference of these two mercury surface level here, H. Okay, H is proportional to the pressure. You can calculate the pressure by giving H. Okay, and then you can either put this in a water bath or sand bath, and then you can read the temperature of the bath, which is the temperature of the gas. Okay, so experimentally, it's proved that the pressure is proportional to temperature. If you have fixed volume, and then if this is a sealed container, then the number of molecules here are fixed. Okay, so volume fixed, number of molecules are fixed, then P is proportional to T. All right. I'm going to just write this down here, maybe on this small window here, just for references. Okay. So the first from experiment is you have the relationship of P is equal to a constant times temperature T, okay? And then secondly, from our daily experience, if you are playing basketball or football, if you change the volume of the gas, say here in the inside the ball here, then the pressure will increase if you squeeze it, right? If you have a ball or a balloon, you will notice that maybe more easily you can tell that from a balloon. If you squeeze a balloon, you feel like the forces pushing back on you is increased. That means pressure is increased, okay? So then pressure is inversely proportional to volume. You can put in equation like this. It's a constant number divided by volume. Okay, so that means inversely proportional, given that you have fixed number of molecules and temperature. Okay. Now, the third here example here is if you pump in more airs into the ball, okay, before and after, if you have a pressure gauge, you can measure what's the pressure inside the ball. You will figure that the pressure it has increased after you pump more air into the ball, right? So given that the volume is already fixed and then temperature is fixed, okay, this is assuming in the process of pumping the temperature doesn't change very much, okay? So then you'll see that pressure then is proportional to, that means a constant number times the number of molecules, okay? All right. So then we have these three relationships between any two of the parameters we have to describe the ideal gas. So you can see that, okay, so then pressure is proportional to temperature, right? It's also proportional to number of gas. Then that means you will do pressure is probably some number times temperature times number of molecular, but inversely proportional to the volume. So that means this, right? Pressure should be equal to a constant number times T times N divided by V, right? So let's call this constant number over here as K. So then P is equal to, so let's call this as K, all right? P then is equal to K T times N divided by volume, right? And if you rearrange the terms, you'll get, so multiply both sides by V, you'll get P times V on the left-hand side. That equals to KTM, right? You can rearrange the terms so it becomes NKT, okay? Now you might find that this equation is kind of familiar to you, right? Because since you learned it in the chemistry of ideal gas law, all right? So let's take a look here on the slides here. So then this is what we have, right? Pressure is equal to a constant number times N times T times V, or rearrange the terms is equal to P times V is equal to N small k times T, all right? So this equation is called the equation of state for ideal gas law, for an ideal gas, or sometimes it's called ideal gas law, all right? Where it turns out that this K constant is the Boltzmann constant, which is equal to 1.38 times 10 to the minus 23 joules per Kelvin. Okay. All right. Now let's take a look on an example here. Okay. So this one says a person's lung can hold about 6.0 liter of air at body temperature, which is about 310 Kelvin. Okay, so last time we took a look on one example. It turns out that our body temperature is about 37 degrees Celsius, right? Which is corresponding to 310 Kelvin. And atmospheric pressure of 101 kilopascal. Given the air is about 21% of oxygen, find the number of oxygen molecules in the lungs. Okay. So, oops. So I think we are going to just use this equation, okay? And then given that K is equal to 1.38 times 10 to the minus 23, Let me see if I remember it correctly. Yes, minus 23 joules per Kelvin. Okay, and then it tells us, it should be easy to do. It tells us P is equal to 101 kilopascal. That means 10 to the third Pascal, right? It tells us the volume is equal to 6.0 liters. That's 6.0 times 10 to the minus 3 meters cube, right? So we have, and then temperature is given as well. Temperature is about 310 Kelvin. It gives us that. All right. So you have those four knowns in this equation, and then the only unknown is m. So you are looking for number of molecular oxygen molecules layer. Okay. You can actually solve for the number of the total air molecule first, and then multiply that by 21, right? 21%, right? That will give you the number of the oxygen molecule then. So let's do this. Let's solve for n first. So rearrange this term, n is equal to then PV divided by KT, all right? Then this is 101 times 10 to the third Pascal times 6.0 times 10 to the minus third meters cube divided by KT, 1.38 times 10 to the minus 23 joules per Kelvin times 310 Kelvin, okay? So that will give you about 1.416 times 10 to the 23 molecules, okay, air molecules. Then oxygen, number of oxygen, let me use N sub O2, symbol for oxygen, should be just 21% of that capital N, right? So 21% times this 1.416 times 10 to the 23, okay, molecules. That equals to about 3.0 times 10 to the 22 molecules. All right. Now, let me know if you have any questions on this one. All right. So you can see it's still a big number. It's 3.0 times 10 to the 22, right? It's a very big number. So that's why, let me see. That's why I think chemists are very smart. So they come up with this idea of say using moles instead of number of molecules, right? So if you use moles, then you'll bring this number down to a very small number, okay? So basically you divide that number, big number, by this 6.022 times 10 to 23 to give you moles, okay? So a mole is defined as the amount of substance that contains as many elementary entities as there are atoms in 12 grams of carbon-12, okay? So 12 grams of carbon-12, the number of atoms there, that's 1 mole, okay? So it turns out to be this guy. This number is also called the Avogadro's number, okay? Capital N sub A, all right? And then the unit is, this is called 1 mole. Okay, so mole is my inverse. All right. So if you use moles instead of numbers of molecules or atoms, then this is your new expression over here then. Okay, so because originally you have PV equal to capital N times K times T. Now you rewrite capital N as number of moles times Avogadro's number times KT, where Avogadro number and K are both constant numbers. You can actually group them together. So Avogadro number 6.022 times 10 to the 23 times Boltzmann constants, that gives you 8.31. Okay, that's called the gas constant R, capital R. All right, if you do that, then capital NA times K becomes R, so then PV equal to M times capital R times T. All right, so this is another expression for ideal gas law or equation of state for ideal gas. I think you guys see this often in chemistry in this expression. Okay, so PV equal to small n times R times T. Okay. All right. Now at the end, let's take a look how hot air balloon works. Okay, so it works the same way as Buoyant's force because air is also considered as a fluid. So last semester, when we talk about fluid, it includes both air or it includes liquid and gas. Okay, both liquid and gas, they are considered fluid. Okay, so in the case that if you have a bottle in water, if you just just empty bottle, you see it's going to be floating there. Now, if you start to put like small rocks inside, you'll see that it will start to sinking down. All right. Now it might be still floating here, but the portion that is above the surface is now smaller. Okay. If you have a lot of rocks in the bottle here, so then it will sink down there. Okay. So you are changing the weight of the bottle by keeping the volume constant, right? So then the density of the bottle with the rock as a whole changes. When you have more density, then this will sink down. If you have less density, then it will be floating. All right. The same thing here for hot air balloon. What you are doing here is you change the temperature of the air inside. Okay. You can do that by putting the more flames, like little fires. Okay, if you heat the air more, then the temperature rises up. Okay, and then if you can bring the temperature down by make the fire smaller, or maybe turn it off. So what happens here when temperature changes here? Okay, so when temperature is high, you see the volume is the same, right? The volume of the hot air balloon doesn't change. Okay, the fact that there's opening at the bottom, that means the pressure inside here is the same as the pressure outside here. Okay, so the pressure stays the same too. Volume stays the same, pressure stays the same. Okay, so this, the left-hand side of the equation stays the same. Then the constant R will stay the same, right? Because it is a gas constant. Now, if you increase T, that means you have to decrease M, which is number of air molecules here. So number of air molecules decreases here, then it becomes lighter, right? So then it will be floating up, all right? If you decrease the temperature here, then number of molecules inside will increase, then it will be heavier, okay? So then it will descend down. So this is the why you can adjust the temperature, how you can adjust the temperature of hot air balloon to make it either goes up or go down, okay? So that's the mechanism there. All right, I guess we will stop here for today. All right, any questions you guys might have before I let you guys go? All right, otherwise I will see you guys on Monday.